Hello, this is Alex recording from Mosaic Works Studios, and today I want to talk about something that I started investigating recently, which is going more deeply into what software engineering is and how it relates to other engineering disciplines. As you may know, I just finished my third book. It's right here. It's called Hands-on Functional Programming with C++. And I just signed the contract for my fourth book, which will be Mastering Software Engineering in C++. And when I started thinking about this, the first question that comes to mind is, what is software engineering? And so I try to find a definition that is working for first to start from engineering in general, and then try to find something that is actually practical, something that I can use to inform my decisions about engineering, or to frame my understanding of software engineering. And so the definition that I ended up with is the following. To me, engineering is applied science used for solving problems. And we can look a bit at other domains and how they do. So for example, if we think about civil engineering, it's mostly about building civil structures to solve various problems, like, going over a river, or transportation, or buildings that serve specific purposes. And what we apply is mostly mechanics and resistance of materials, things like this. So deep specialized scientific disciplines. If we think about electrical engineering, we apply things from electromagnetism to build circuits and devices. Nowadays it's even more, you go into quantum mechanics and things like this. Industrial engineering is a bit different, because what it does is it optimizes processes. It optimizes production in industry. And how does it do this? It applies system thinking and system theory. So you see, this definition fits many of the engineering domains, and it can be used to inform kind of frame the ideas around these domains. And if we look at engineering in general, what do engineers do? They build something, or they optimize systems. Another interesting thing about engineering is, okay, they use existing science, but they also go beyond it. There is a famous quote by Albert Einstein saying that scientists investigate for which already is, engineers create things that don't exist yet. So in order to do that, we've been building bridges before we actually had a theory of gravity or a theory of resistance of materials, but we were still able to build bridges. And this is mainly possible because engineering goes a bit further. It doesn't try to understand necessarily how science works for that domain, but it tries to use kind of the empirical observations and expand on those, such that you build things that actually last. And so in order to do this, you also need to do things like formulating a hypothesis, doing some prototypes, trying things out, so that you test your various ideas. But the goal is different than in science. Although the method seems similar, the goal is different. What engineers try to do is to build something that works. What scientists try to do is to deeply understand and create some math equations that can predict how these things work. So this is kind of the similarities and differences, and this is where engineering kind of stays from my point of view. Okay, so now if we are thinking about software engineering, so it's clearly that we build software programs. Sometimes they interact with outside systems, sometimes it's a combination of hardware and software, but for simplicity we'll just focus on the software part. So now the next question is, what is the science? What is the science behind software engineering? What kind of science do we apply in software engineering? And if you look at existing literature, I think the most common answer, the answer that would come to your mind is math, right? After all, a computer is basically a big, very repeatable mathematical machine. We have things like, binary language, pure functions, lambda calculus, Turing machines. These are all mathematical concepts that were then translated into computers and programming languages and other things. But to me, this is not a fully satisfying answer. It feels like math has been used to create the platforms that we build upon when we build software. So it doesn't satisfy me. And in fact, I have a proposal. I believe that we need another type of science. A science that already has some things developed, but a science that needs to get even more developed. And it's about the science of knowledge. So let me go a bit into more details. Why do I believe this? So first thing that we need to remember is, let's look at code and let's ask ourselves, what is code? You could say that code is a mathematical structure, but I don't believe that's fully what it is. Code is also something else, and I've long had this intuition that code is very precise encoding knowledge. So for example, if you have a device driver, a program written to read and write data to a device, all the knowledge about how that device works, how it integrates, how it works as a black box, so what are the inputs, what are the outputs, what it does, when it does what it does, these are all encoded in your code, in your device driver code. If you write an e-commerce application, everything about how the processes for selling and the policies and the rules for discounts and all this kind of stuff, everything is in there. It's in the code. So because this is knowledge, it's also code is knowledge, but then in addition it's also very precise knowledge. Why is it very precise? It's easy to answer to this. You cannot give fuzzy code to a computer. It won't know what to do with it. So we have very, very fuzzy requirements in the beginning, and we end up with very precise encoded knowledge. So this is interesting because I believe that software engineering is mainly about taking these fuzzy requirements refining them until they become very precise in coding knowledge. It's not everything that software engineering is about, but it is a part of it. A second thing that I believe software engineering is about, it's about maintaining the knowledge as time passes. So as time moves on, you learn more and more about what you're trying to achieve. And often the code, the knowledge from the code, it's not kept up to date. And after a while, it started being spread in various parts of the code. And even if the knowledge is there, you cannot actually go inside, look at the code and recover the knowledge, understand what's in there. Because it tends to spread out or to organize in a very weird manner, depending on how it evolves. So I believe that software engineering is about the practices that allow us to maintain this knowledge structured inside the code so that we can actually recover it at a later time and understand it and so on. And the reason we want to do this is to optimize development, right? Typically when you build a bridge or a car, you have a design process and then you have the build process, and then the bridge is there and it stays there for a number of years, or the car can be used, mass manufactured and then used for a number of years. When you build software, you keep changing and fiddling with it for a long period of time until people no longer use it, and then the changes kind of phase out and you don't want to change anymore. So this is a big difference between, the kind of engineering we do for software and the kind of engineering we do for other things. Right. So therefore I believe that we need a science of knowledge. How would this science of knowledge look like? And just allow me to advance my notes a bit. We already have a few things around a science of knowledge. We have, first thing that's interesting is information theory, where we have already defined what a bit is. I will just pick this example because it's fundamental. If you look at the definition of Shannon for a bit, if we translate it into a knowledge frame, it will be, what a bit is actually an answer to a yes-no question. It's more than that, because what Shannon was looking for was a way to transmit information, a way to do communication. And a bit is actually about the entropy in information. And what he says is that yes, no should be of equal probabilities. But for us, when you think about strictly in terms of knowledge, it's enough to think about a bit as the answer to a yes-no question. And this leads us to a very interesting situation, because all the code that we write turns into bits, and then those bits actually, each of them is an answer to a yes-no question that we try to settle while developing the code. Right? Fairly interesting. This is one, let's say, very basic, very fundamental way in which knowledge is stored in code. The second area where we can bring in some more ideas about knowledge is an old branch of philosophy called epistemology. This is a branch of philosophy that tries to answer questions like what do we know? How do we know that we know? And right now we cannot take a lot, at least I don't know specifically the things that we could take out of this and turn it into a science of knowledge. But it's there are definitely some fundamental things there that are worth discussing. And often science has come up from a branch of philosophy where people were asking various questions, answering them, and with science, it informed scientific experiments or scientific hypotheses, which then were proven or not. So it's definitely an interesting area to look at. A third one, which is maybe more practical, is the way OWL stores knowledge. OWL is Ontology web language. It's a language created with the goal of storing knowledge related to specific domain, even to fairly complex domains like healthcare, anatomy or physiology or or diseases or things like this. And I've actually seen applications of OWL with healthcare, and I found them fairly interesting. Now, what we look at when we look at OWL, what it has fundamentally is nodes that represent notions and relationship between nodes. Each relationship being of a specific type. So you can have relationships such as has a, is a, but also relationships like contains, larger than, smaller than, many types of relationships. So in a way, OWL is an extension to object-oriented programming, to object-oriented design, to how we structure our code in an object-oriented code, in an object-oriented way. But as you can see, these are some of the areas that we can go from, but they don't give us enough to apply. We are missing a lot of things. We have a number of big questions. For example, one question: is there a normative representation of knowledge? So if I'm trying to build, let's say, an e-commerce application and I know some of the things about the application, is there a way that I can structure my knowledge inside the code which is optimal, or which is let's say normal, in the sense that any other type of any other structure can be passed through, first transferred into this normal form and then transferred into other forms if we desire to. Another thing is, how do we effectively evolve the representation of knowledge when we learn something new? This is a big problem in software, right? We get into technical debt because we learn new things, but our code is not structured accordingly to the new things that we learned. And so we've devised a bunch of ways to kind of allow us points of expansion, like dependency injection or and interface inheritance and things like this. But these are not, we're not sure that these are the most effective ways of doing so. So maybe the question leads to a deeper question, which is how can we actually store and evolve the knowledge, structure and evolve the knowledge as the time moves on. Another one is how can we validate a representation of knowledge against the knowledge itself. And this is the problem of, testing, validation. If we have some kind of knowledge that we refined and so on, and then it gets turned into code, but then how can we effectively validate it? How can we refine knowledge from very fuzzy to very precise in the most effective manner? We know that iterations are something that helps, and they are used by all other types of engineers as well. But we don't know whether this is the most effective, the manner that we use is the most effective, and we don't know whether there are more practices that we can use to actually do this refinement. Okay, so this is where I am right now. I plan to read some more about this topic. I plan to, anyway, once I start writing the book, things will move forward. It will be very interesting to explore these ideas and to link them to existing practices. I hope this is interesting to you. I've left out many things, for example, implementation, risks. There are many other things that engineers do and software engineers do. But I felt the need to record this video because I found these are some very interesting ideas. I think these are new ideas. It's a new perspective towards software engineering. And I have to admit that I'm curious of what people think about this. So I hope you find this useful. If you have ideas around this, please comment. And if you want to support me, this book is on Amazon. Go and check it out for you or for a friend. Who knows? Maybe we'll have some more things to discuss. Thank you, and hope to see you soon.